Very good afternoon, everyone. I welcome you in the post-lunch session of the day. And in this session, Professor Sharma will continue his technical talk on hydrogen storage technologies. Professor Sharma, ma'am, am I audible?
Yeah. Actually, that message was coming that the host will allow you to unmute. Okay, fine. I will
Can we start the session, ma'am?
Yes, I will share my screen. Is this visible?
Yes, ma'am, it is visible. Yes, ma'am.
Thank you. So in this session, I will very briefly talk about the other aspects of hydrogen other than the production. Production we have already seen in the morning session. In this part, I will talk about storage, how we can transport it from one place to another, and what are the safety features that needs to be taken care of when hydrogen is being produced, it's stored, it's being transported, or it is being utilized. So whatever method which we use for producing hydrogen, whether it is renewables based or whether it is fossil fuel based hydrogen production, either it could be in a centralized plant, it could be in a big industry, or it could be a decentralized plant, whether it could be a smaller reformer or a electrolyzer near a refueling station. So the way, like the amount of hydrogen which is being produced may not be always consumed at that pace. It may not be consistent with the demand. So when the supply and demand mismatches, there is a requirement of storage, whether it is hydrogen or any other form of energy. Now, the storage is the biggest bottleneck in the entire hydrogen value chain. Now, what are the basic issues associated with hydrogen usage? The major problem is the storage. Now, why is it a challenge? Let us see certain numbers. Hydrogen has several advantages when we consider it on the mass basis. So per kg, it is having a higher energy density. Like it is 120 megajoule per kg on a lower heating value. And this is more than double that of the CNG, natural gas, which is for methane, it is 50 megajoule per kg, for LPG, 46 megajoule per kg, gasoline, 44 megajoule per kg, and same situation is on a higher heating value basis. So on a mass basis, it has advantage. It is much more richer as compared to the other fuels in terms of energy density. But the scenario completely changes when we consider on a volume basis. If we consider on a volume basis, hydrogen at normal temperature pressure conditions, density is very low. It is the smallest molecule, lightest molecule. It has very high diffusivity, and all that makes it very difficult to confine or contain in a vessel or a storage unit. Like if you try to store it in 1 liter, you can only store an energy equivalent of 0.01 megajoule. But methane, we can store even much higher. Let us compare with gasoline, which are our conventional fuel, petrol. So the energy density on a volume basis, it is 32 megajoules per liter. So that means if we compare hydrogen and gasoline, 3200 times more energy can be contained in 1 liter of the tank. And diesel like 3600 times more energy. But this is at normal temperature pressure. That means if you want to store hydrogen in a container, the volume required will be very high. How much? If you want to store 1 kg of hydrogen, the volume required will be 11 meter cube or 11,000, accurately 11,940 liters of volume will be required to store it. Now, if you want to still make it conformable or reduce the size volume of the container, what you have to do is you have to increase the pressure. Now, if we increase the pressure, let us say at 20 bar, the energy density improves. From 0.01, it becomes 1.8 megajoule per liter. We further increase pressure, say 350 bar, then it is 2.84 megajoule per liter. And it keeps on increasing as we increase the pressure. Another way to make it more dense is we can liquefy it. Under 1 bar pressure, if we liquefy it, convert it into liquid hydrogen, the density improves 70.9 kg per meter cube, or per liter we can store 8.5 megajoule of energy. Now this seems to be quite reasonable. As we compare with the gasoline or diesel, this is about 1/4 of that of gasoline. We can still change its phase. We can store in solid state form. In that case, the energy density further improves, even higher than the liquid state storage, depending upon what material we are using. It is higher than 100 kg per meter cube. Now, when we have seen these numbers, it seems that conformable storage of hydrogen in a lower weight, in a volume, is the biggest challenge. And that is challenging when it comes to vehicular application or mobile application, because the amount of space available is limited there, and you have to carry that along with you when you are moving. However, this is not that great challenge when it comes to stationary state storage. So when you talk about storage, we have to see several parameters. These parameters are like the cost, not only of the fuel. In the earlier part, we have seen the production cost. Here we have to also see tank cost, the balance of plant cost, and that we will see what else is included in that cost. We have to see how durable is that system. So if it is for vehicular storage, roughly it is considered 150,000 miles of running of the vehicle, and then it should still have the same life of the tank. So that durability should be there. It should be operable under different conditions. It should not happen that a vehicle you are using in Rajasthan, then the tank system has to be replaced when you are using in North Kashmir. So it should be operable under a wide range of conditions as well. The charging and discharging rate or the refilling time should be at par with the conventional gasoline-based vehicle. Duration of storage, whatever we want. It should not happen that we have filled in the tank and it gets emptied, vacant. And that happens in case of liquid state storage. So there the dormancy plays a role. It should be faster in response. Your storage unit should be faster in response. Like it is again important when it is up to braking in a vehicle. So when you are stopping the vehicle, it should immediately stop the fuel flow to the fuel cell, or it should immediately start the fuel as you turn on the vehicle. So the faster response is essential. It's transient response. There should not be decay in the properties, performance, efficiency, the quality of fuel, efficiency. So these are several other parameters that needs to be considered when we talk about a storage system. Before going into these storage systems, let us quickly understand the phase diagram of hydrogen. So it has, under normal temperature pressure condition, it is gaseous. It has a triple point when all the three phases coexist. So it is at 13.96 Kelvin and 7.36 kilopascal. And it has a very small region, which is the liquid state region. So when we go to the critical point, 33 Kelvin and 1 megapascal, 1.313 bar, beyond this, if we further increase the pressure, we cannot liquefy it. So then there are different other regions, like there is a solid region. So you can, before that, so this happens at it converts into liquid hydrogen at 20 Kelvin or minus 253 degrees centigrade. If you further cool it down to 14K, it will convert it into solid hydrogen. Before that, like it is a slush hydrogen. It is a solid and liquid inseparable system. If you further take it to lower temperatures, then there are 4 different metallic hydrogen phases which have been obtained, which were actually identified in 1935 and then observed in 1996. Then it goes into plasma phase. So like you keep on increasing pressures and temperatures, you will get a different phase of hydrogen. However, we are not interested in that, because there we talk about 10 raised to power 11 bar of pressure, or 10 to power 3 to 10 to power 4 temperature. So that is not of practical importance. Here, what we are interested is in this particular smaller region comparatively, where it operates as a gas or liquid. Even solid, that temperature is very low. So this is not the solid physical hydrogen, molecular hydrogen we will be talking about. Now, another thing which is important when we talk about the compression of hydrogen is the compressibility factor. Like any pure substance, molecular hydrogen, it has 2 state variables, and using those 2 state variables, the rest of the other state variables you can find out. So there are different equations of state which you can use to find out the corresponding other values. Now, hydrogen, under the conditions of low temperature, low pressure and high temperatures, it follows ideal gas law. But as the pressure increases, when we are talking about higher pressures, 200 bar or 350 bar or 700 bar, the deviation is higher compared to the ideal gas behavior. So we have to use other models like the van der Waals equation, or the another way could be to find out the compressibility factor. And compressibility factor is nothing but it tells us how much is the behavior deviating from the ideal gas in the actual practice, in the real case. For example, just to point out here, this is the compressibility factor, and you can find out this experimentally, and there are plots available. Let's say if at room temperature and 300 bar, we hit this line at 1.2 value of compressibility factor. So under these conditions, when you are compressing it under ambient condition of temperature to 300 bar, the value is 1.2. That means if we have used ideal gas equation to find out the mass of hydrogen stored in the tank, we could have overestimated by 20%. So all those corrections have to be considered before we find out like how much is the amount of hydrogen stored at a particular pressure, or what is its energy density. When it comes to liquid hydrogen, we will come back to compression again. Some properties we are revising. Now, when it is liquid hydrogen, so diatomic molecule, it has 2 protons, and their elementary particle spins could be either parallel or anti-parallel. When it is parallel, it is orthohydrogen. When it is anti-parallel, it is parahydrogen. Under normal temperature pressure conditions, this is the equilibrium composition, where it is 75% of ortho and 25% of parahydrogen. But when you are cooling it down to make it into liquid hydrogen, the equilibrium composition at 20 K is this orthohydrogen converts it into parahydrogen, and the parahydrogen is more than 99%. Orthohydrogen is less than 1%. This hydrogen is a lower energy state. So that means when this conversion happens from the room temperature to liquid hydrogen temperature, which is 20 K, energy will be released. So the process is exothermic, and you have to take out that heat. So you have to fight with 2 phenomena. One is you have to lower down the temperature. At the same time, this exothermic heat which is released, you have to take that heat out also. So that means higher is the expenditure or energy expenditure associated with liquefaction. Now there are different ways. So some of these we have quickly talked about. So there are ways of storing hydrogen. It could be in the physical storage, where you are storing hydrogen in the molecular form, in compressed storage tanks, in the liquid form, or this can be stored in the molecular form on high surface area materials, where the molecules, they get adsorbed onto the surface of these materials. It could be chemical storage, where the molecule breaks down into atom and forms a bond which is stronger than that being formed in the adsorption based materials, forming either a metal hydride or a chemical hydride or liquid organic hydrogen carriers. So these are broadly the ways in which we can store hydrogen. Now, when we talk about the storage method, as I mentioned, the vehicular storage is more challenging and more demanding. And it is not the only the weight of the hydrogen that needs to be carried in the tank, there are associated several auxiliary components, which includes the vessel in which it is being carried. This includes the various valves, fittings, tubings, monitors, sensors, cooling devices, the health monitoring systems, the leak detector sensors, and there are various other associated accessories, compressors when it is like at a higher pressure. So several other things that becomes a part of the storage unit, and all that makes the system. Now, which particular method will be good enough to be commercialized, or the researchers should go ahead, have a green flag to be taken it up to on a larger scale? That all is, for that a criteria has been given by the US Department of Energy. That is in terms of how much weight of the hydrogen which is being stored per unit system weight, or whether it is per unit volume of the system, cost of the fuel as well as the system, at what temperatures it should operate. For example, just quickly some numbers I will mention here. So when it comes to how much amount of energy in terms of hydrogen is being stored per kg of the system, then it is 0.055. That means 55 grams per kg of the system should be stored, and that is the target for 2025. And finally, like 65 grams. Temperature, it should be operable in -40° to 60° as well. So ambient could be very low temperature in Russia, or it could be in Rajasthan, a higher temperature. Inner temperature will always be higher compared to the external temperature. These are in terms of at what rate hydrogen should be dispensed. It should come out and should be provided to the fuel cell system. And these are how long it should be stored. So there are various targets associated with that. Based on these, the researchers, they come up with their own devices, their systems, their materials. And then based on these targets, they can judge whether that particular system is appropriate for scaling up or not. Now, starting with the first method of storage, as we have seen that industries, they are using millions of tons of hydrogen, and it is not possible to store in compressed state storage. The tanks which we will be describing, or the solid state storage, we require very large area reservoirs to store that hydrogen. So that can be stored below the ground in places where we have ample amount of space and where we feel that it will not get contaminated. So like we can have salt caverns or depleted oil and gas reservoirs which are now empty, and we have taken out the gas and oil from there, or aquifers. So these are three different modes in which we can store very large quantities of hydrogen under the ground. Now, what we need is to find out how much amount we want to store in these underground storage facilities, how long we want to store, at what rate these facilities should give back that hydrogen, and whether we have that geological facility available or not. Under Indian conditions, we have a problem with the availability of these reservoirs, but globally, these are being considered for, and there are several large reservoirs, preferably salt caverns, because aquifers are least studied ones, and depleted oil and gas reservoirs, they contaminate the hydrogen. So salt caverns are the most studied ones for underground hydrogen storage. The other methods which we talked about was the gaseous storage. These gaseous storage is done in high pressure tanks, and the commercially available tanks which are integrated with vehicles, Toyota Mirai, Honda Pyrus, these are like pressurized tanks, type 3, type 4 tanks, which can store hydrogen at a pressure of 350 bar or 700 bar. Cryogenic tanks are also available. These are super insulated vessels. But the process is highly energy intensive. There are other challenges that we will see. And then there are solid state routes also for storing hydrogen, which has a benefit compared to the gaseous and liquid state storage, that it has a very high volumetric energy densities. We have seen the energy density per unit volume in the first slide. At the same time, this is a safer method for hydrogen storage. Now, when we have to store it in gaseous form, we have to see that the hydrogen, it is at a very high pressure. If we see the pressure in our household, let's say the pressure cooker, what we talk about is 2 bar. And here the pressures we are storing hydrogen is 350 bar or 700 bar. So the material which is storing that hydrogen at such a high pressure should have that strength to confine that hydrogen at those pressures. Other than that, since hydrogen has certain peculiar characteristics, like it can react with different materials, it can cause embrittlement, where the metals, when are exposed to hydrogen over longer time, they lose their ductile nature and they become brittle, and that can lead to failure. So because of all those reasons, certain special materials need to be used for storing hydrogen. Austenitic stainless steel, certain aluminum and copper alloys, and special materials are required. And these tanks are designed so that they should be in a specific geometry, although spheres are better because, but the conformability comes from a cylindrical tank. Since we are increasing pressure, there is a relationship between the wall thickness and the pressure. Wall thickness will increase as the pressure increases. But if it is a metallic tank, that will make it more and more heavier. So there are generations of tanks like type 1, type 2, type 3, and type 4 tank. Type 1 tank are all metal tank. Type 2 tank is wherein partially you have a fiber wrapping onto the hoop side. Type 3, you have the inner metal lining, which is in the form of mesh and a fiber wrapping. Type 4, where you have an inner polymer, we eliminate metal so that the tank weight reduces further, and a carbon fiber wrapping. Weight is important here because if it is all metal, the strength is coming by increasing the thickness of the tank, and that adds up to the weight. However, type 4 tank, both the materials, the inner layer, which stops the flow of hydrogen through it, which has a very low permeability for hydrogen, is made up of high density polymer, and the outer layer, which is a carbon winding wrapping, that provides strength to the tank. So this storage tank, which are used for storing high pressure hydrogen, they serve multiple purposes. They have to not only contain hydrogen, they have to control, regulate its flow, they have to monitor that there should not be any leak, should distribute in the associated piping, meter, refill. There should be an arrangement for refueling also when it is connected to the refueling station, and they should sustain that high temperature pressures as well. So that serves multiple purposes. As I mentioned that there are 4 different classes of tanks. Type 1, which is made up of all metal. These are the industrial gas tanks, which you would have seen red color painted, which are there in the laboratories. Then type 2, which has a pressure, this is a pressure vessel, which is thick metallic inner liner, and then only the hoop area is wrapped with the fiber resin. Then type 3, which has a metallic liner and a fully wrapped one with the carbon fiber, and the type 4, which has an inner polymer and outer wrapping with the carbon fiber resin. So as we go along type 1 to type 4, the weight reduces, but the cost increases. For vehicular application where the weight becomes an important, in that case, type 4 tanks are being used. The second method for storing hydrogen is we can liquefy it. So we can liquefy it through a process which consumes less amount of energy. So it could be either so if thermodynamics, we all know that the process which has an isothermal compression and isoentropic expansion, that will result in the lowest amount of energy. So gaseous hydrogen, it undergoes, this is an ideal liquefaction process, but in real case, it deviates. So it becomes a polytropic process, where we have to go through a sequence of steps. It has to be compressed to a higher pressure, that is 30 bar. Then it has to be cooled down in a liquid nitrogen heat exchanger to bring its temperature down to 80 K. Then it has to undergo an expansion in an expansion turbine where its temperature goes below 30 K. And then finally we have to have a, in an expansion turbine, finally a Joule-Thomson valve is used to lower down its temperature to 20 K. Now the two most energy intensive steps involved in the process is the compression to 30 bar and then its expansion in an expansion turbine. These eats up the energy, most of it. So if we typically see a process of liquefaction, about 30 to 40% of its energy content goes in liquefaction. At the same time, when it is in liquefied state being stored in a container, so these are super insulated tanks which are to be used because we are storing them at a temperature of 20 Kelvin and the delta T between the ambient and the liquid hydrogen is very high. Now, when this temperature difference is very high, howsoever good insulated vessel you may use, there may be a heat leakage from the ambient to the tank. And when there is a heat leakage, certain amount of hydrogen gets evaporated. That evaporated hydrogen, it is essential that needs to be relieved, that pressure needs to be relieved, else these tanks are not meant for high pressure operation. These are meant for insulation with higher insulation. So if the pressure increases beyond a certain limit, it can lead to rupture of the tank. So always the system operates as an open system. And then the amount of hydrogen which evaporates, which is left out of the system, that is a loss, which is known as a boil-off loss. Now, depending upon what is the system size, that can range from 0.3% per day to 3% per day. And this is enormous. Enormous in the sense, if you have a liquid hydrogen tank being filled in a container, and if you leave it for a few days, you go for a vacation, come back after vacation, you may find the tank empty. So that is what the biggest challenge, boil off, as well as the high energy intensiveness of the process. And that is the term dormancy, which we introduced in the first slide, is for how long it can be kept in the liquid form without evaporating. So without first release of hydrogen from the system. Now the other method could be we store in the solid state form. Now this is the most safest method because neither we require very high pressures like that was in the case of pressurized vessels, nor we require very high temperatures. So what we do here is either we store it in a physical form like a molecular hydrogen without breaking up it into atomic hydrogen on the surface of high surface area materials. These can be carbon-based materials, metal organic frameworks, or zeolites, or several other materials. Or hydrogen molecule can break up at the surface of material to form hydrogen atom and then sit in the interstices, or it can form a bond forming chemical metal hydride or complex hydrides. So these are the different ways in which we can store hydrogen in the solid state form. For such a storage, there are certain requirements that needs to be met, that the amount of hydrogen which is stored in a container per unit mass, per unit volume, it should be high. Such materials which store hydrogen, like on a chemical basis, they give that hydrogen supplying when we supply certain amount of heat. So that heat of formation or dissociation, when it is stored in a chemical form, should be moderate as well as the pressure of operation. The system should be reversible, it should be faster in response, it should be stable under the different operating conditions, under ambient conditions, cyclability of the materials being used, cost and safety. These are again of prime importance. So there are different materials which are available like carbon nanotubes. So hydrogen can in the molecular form H2 can store in the pores. It can store onto the surface of different materials. It can be stored by means of chemisorption when you have metal hydride, hydrogen molecules comes onto the surface, breaks into hydrogen atom, can sit into the interstitial space, or hydrogen can form a bond. Like this is then ammonia, borane, nitrogen forming bond with 3 hydrogen, boron forming bond with 3 hydrogen, or complex hydrides where have an ion having a 4 hydrogen atoms. So there are wide variety of materials which can store in a physically bound hydrogen, like the porous carbons, carbon nanotubes, zeolites, metal organic framework, polymers of intrinsic microporosity, and they have a different storage capacity. When we talk about storage capacity, that is the amount of hydrogen being stored divided by the amount of hydrogen plus the material weight. So it can be high, like 6.9 weight%, but then these materials store at a lower temperature because the bond formed is a weak van der Waals bond. It can be stored in the form of metal hydride, and there are different class of metal hydrides which are formed. Like these can be metal hydrides are when a surface is exposed to hydrogen, all the elements, most of the elements in the periodic table, they form hydride. So that bond which the hydrogen form with the metal, it can be ionic, covalent, or metallic. These can be either complex hydrides, where the subcategory could be alanates, borohydrides, amides and imides, or chemical hydrides. When it comes to complex hydrides, there are different classes of materials that just now I mentioned. Here, since the bond is being formed with the lighter metals, the overall weight of the material is lower. So either the first group or second group materials are used. So as such, these are lightweight materials. But then the problem with these materials will be that once you get that hydrogen out, it is difficult to put that back. So these are sometimes known as one-pass materials. And they have different limitations which are associated, like kinetic and thermodynamic limitations. So they give that hydrogen in different steps. Like these are some of the examples: sodium alanate or lithium alanate or magnesium alanate. When it comes to another class of materials, which I just now told, that metal hydrides, a metal can react with hydrogen to form metal hydride. They have very high volumetric energy capacity, and these are safe to operate because there are hydrides which can store under ambient conditions close to room temperature. The pressure at which they store is also close to your 1 bar. So there are wide range of materials, and you do not require very super insulated vessels or thick walled container to store them. Just to quickly give you an idea, when a metal reacts with hydrogen, it forms a hydride. So a very simple reaction. And then when you want that, you have to do the reverse of it. That means when metal reacts with hydrogen, forming a metal hydride, this is an exothermic reaction, releasing heat. And when you want that hydrogen back, which is being stored in the metal hydride form, you have to supply that heat. That means it is an endothermic reaction. And there are different materials which are available. And there are different classes of such materials which are available, which can store hydrogen reversibly. That is the biggest advantage of metal hydrides, that they store hydrogen reversibly. And you can have several cycles of operation without performance degradation. Just to give a brief idea about what we are doing in this area research at IIT Bombay, we are working from a very nanoscale on molecular level using density functional theory. We design the materials, we look at the different alloys, we look at the different dopants which could be possible, substituents to enhance the performance of the materials. Once we identify a particular suitable material, we go on for synthesis of that material. We make it on small scale, go for characterization of that material. Then we make it on a larger scale. And then we finally put it in a device, storage device, and integrate it for various applications. So we are looking at materials research from small scale to large scale, from designing the material to implementing it for an application. We are working on systems design, where we go from the systems computational studies to see how a system should be designed to store this metal hydride, to fabricating it, studying its performance, iterating it. So we go from selection of materials to tuning these materials to get the appropriate performance, designing systems, designing the tanks, that rigorous simulations, modeling and optimization we used to do. Finally, we fabricate the systems and then we integrate. So from materials, we go to systems design, to fabricating systems, and finally integrating those systems. As I told you, the one process is exothermic, another process is endothermic. So a lot of thermal management is involved. So whatever heat is put inside the reactor, that has to be taken out, or the required amount of heat has to be delivered. Since these metal hydrides have a poor thermal conductivity, we have to work on several fronts. Like we have to improve the thermal conductivity, we have to enhance the heat transfer surface area by using several heat enhancement surfaces. We have to improve onto the heat transfer coefficient. So in our lab, we are working on different types of systems with different heat exchanger designs. Just to show you some of the reactors that we are working on, we have systems which can store 5 kg of metal hydride alloy. We have systems wherein we can store 10 kg, 25 kg, 50 kg, another 50 kg systems. And these are specially designed for various other applications. Like the 10 kg alloy can store 120 grams of hydrogen, and it has a 4 kilowatt hour of energy it can supply. 50 kg system, this was specially designed for ISRO, that can store 900 grams of hydrogen, and it has a capacity of 30 kilowatt hour. Another one which we are working on is 100 kilowatt hour. Then we integrate these systems for different applications. Like this is a thermal energy storage system wherein you have two different metal hydride beds, a high temperature metal hydride bed and a low temperature metal hydride bed. High temperature one takes solar energy to release that hydrogen and store in a low temperature metal hydride bed, while at the night time, we can give a low grade heat to get a high grade heat back from such a system. Like the large scale synthesis, you can see this is one of the facility which is we are having in our lab for large scale material synthesis. And this is the same one, that different reactor design. Now, these are the different options which you can use to store hydrogen. But when at the point of utility, you have to take that for the utilization, whether it is from the production plant to a large scale storage plant, or from a storage unit to a refueling center, refueling station, or from one centralized production plant to an industrial application, we need to carry that hydrogen. And there the hydrogen transport plays a major role. Now we can transport hydrogen in either liquid form or in gaseous form. Solid state form transport, although it is being considered, but it has not reached to that level of commercialization. So the two option remains is we have to make it into gaseous form, pressurize it, and then carry it by means of either tube trailers or by means of pipelines. We can have trucks carrying gaseous hydrogen, or it can be liquefied, converted into liquid form. It can be then taken through road by means of ships or in terms of high energy density materials, ammonia, methanol. So that hydrogen can be converted into other fuels which are having higher energy density. And then it can be either reformed at the point of usage or separated from this at the point of usage. But then that energy which we will be requiring for during the transportation, we can save in that. But then there is a trade-off. The amount of energy you are going to spend in converting it to high density material or then converting it back to hydrogen as against the energy which is spent in the transport. So always there is a trade-off, and based on the capacity, amount of hydrogen that has to be taken across, or the distance at which it has to be transported, all that plays a decisive role. So the different methods of transporting is you can take it through gas pipelines, or we can compress it on a compressed hydrogen trailer and then take it to the refueling station like the CNG, or we can convert it into liquid form, take it on a truck, super insulated trucks, vessels on a truck, and then take it to the point of usage. Now, which method will be useful? That depends upon how long we have to transport it. So the delivery distance, it depends on how much quantity that to be transported, whether it is a rural region or whether it is an urban area, whether the other facilities associated will be available or not. Now, when it comes to gaseous hydrogen transport, what we have to do is, from a centralized hydrogen production plant, that needs to be taken through a transmission pipeline or a distribution pipeline. But since that pipeline network will be very long, kilometers long, so definitely there will be a pressure drop. So we have to have compressors at distances to again take it back to the same pressure. So after every 200 kilometers, a compressor will be required. And again, the compression itself has a process which takes up certain amount of energy. Ideally, it is 8 to 10% of the energy goes in the compression. That's why, like in the morning when we were talking about the hydrogen production, any production plant which supplies hydrogen at a higher pressure has an advantage because we can save in terms of the compression power. So this is one way of doing that. We can transport it through pipeline, but there are problems associated with the pipeline transport. And these are like the pipeline, laying down a pipeline cost is very high. So it is like 1.4 to 2 times higher than laying down a natural gas pipeline. And then this variation could be because the steel prices, these are volatile. The land usage will be different. In different countries, the corresponding prices may be different. At the same time, the amount of energy, because the density of hydrogen is lower, the amount of energy which we will be carrying through these pipelines will be lower because of the lower density. So we have to provide certain energy to push that hydrogen. That means the energy which is required to move the hydrogen across pipeline will also be higher. At the same time, the cost of the material will be different compared to the natural gas pipeline. The reason being, hydrogen shows an embrittlement behavior when it comes in contact with the different accessories, with the different pipeline, walls, manifolds, sensors, tubings. So the material should be special materials which does not undergo hydrogen embrittlement. Now there are 3 options which are being looked by the researchers. One is either completely build a new dedicated hydrogen distribution pipeline or use the existing natural gas pipeline, but then you have to blend it to a certain percentage without affecting the properties of the material of the pipeline. Completely use the natural gas pipelines, which is little difficult. Only the options could be either lay down a new pipeline network or blend hydrogen to a certain percentage. So the major problem remains with the pipeline transport is a very high capital investment cost. There are materials challenges because of the embrittlement, and then you have to have leak detectors because it is a long distance which you have to carry, and hydrogen is a flammable gas. You have to have a leakage and monitoring system, sensors at every interval of time, distance, and compression also to reduce the pressure drop. Or these gaseous hydrogen can be transported by means of trailers through road. But since the density is lower, the pressure required will be higher. You can only transport a smaller quantities using trailer transport. So if the distances are like less than 200 kilometers or quantity is 500 kg, then this trailer transport would be efficient. If the distance increases or the volume increases, then liquid hydrogen transport will be more economical. And if the distance is very, very large and the volume to be carried is higher, then in that case, pipeline could be used. But the pipelines, laying down the pipeline, the capex is higher compared to the opex. For the other methods, capex is lower, opex is higher. Like the liquid hydrogen, the installation of the equipment may not be that great compared to the energy penalty, that operating cost associated with it. So like the tube trailers which are already there, super insulated vessels, these can be carried through ships as well. So this was about how we can transport hydrogen. But when it comes to hydrogen, the very common fear that comes to a wider mass or the consumers or the customers that will be using in future is the safety associated with hydrogen. And that is very important as well. There are certain properties of hydrogen that makes it further essential to be very careful about using hydrogen. It is not that it is a completely, it's a fuel which cannot be used. It is that the same protocols that we follow for any conventional fuel, a similar caution needs to be taken care of when you are using hydrogen. The properties there are certain properties which makes it which makes it more disadvantageous when being using it as fuel. But there are properties which has both advantage and disadvantage. Let us quickly look at those. As compared to the other fuels, hydrogen has a very wide flammability range. Now, what do we mean by flammability range? That as concentrated mixture as high as 75% of hydrogen with the oxidant and as low as 4% in air being acting as oxidant there, can lead to a flame or combustion. So that means it has a very wide flammability range. A linear mixture can also ignite and a concentrated mixture also can ignite. However, this range is very narrow when it comes to petroleum or methane. So this has both advantages and disadvantages. Disadvantage, when it is to be used as fuel, if there is a leakage, then anything can burn. A linear mixture as well as a concentrated mixture. It has an advantage when it is used in combustion. A linear mixture can also combust completely. So complete combustion, a better efficiency of combustion can be achieved. It has a diffusivity, which is very high as compared to petroleum and methane. And this is important because this has an important safety asset. If in case of leak, it diffuses very fast. So the advantage is it rises vertically and it diffuses, gets diluted very fast. So as such, any leak, if there is, there gets lesser chances of its ignition when the diffusivity being very high. It's an order of magnitude higher compared to the other fuels. Its ignition temperature is higher. That again is an advantage. At the same time, disadvantage. Advantage in the sense that it may not ignite on its own because the temperature required for its auto ignition is very high. But then you cannot use it in auto ignition engine. Its ignition energy required is very low. It's again an order of magnitude lower. And that is a disadvantage again as well as advantage. Disadvantage in the sense that if there is a hydrogen leak, even a small friction from a surface, the static charge itself is sufficient enough to ignite. And this becomes an advantage when it comes to combustion used in an IC engine. Rest of the properties, again, we may not be much interested about in the fuel properties of the hydrogen. Now, what are the safety features that we need to consider when we are using hydrogen? There can be different types of failures, and we have to be careful because if we look back into the history of different accidents which have resulted from hydrogen, most of these have been due to the human error. So the possibilities in which the accidents can happen is that there could be a mechanical failure or material failure. Tanks which are seamless are more desirable. Reason being, when there is any welding point or a point wherein there is a hairline or even lower than that crack can propagate and that can lead to material failure. So one reason of such events, catastrophic event, could be a mechanical failure. It could be a corrosion attack. This is because of the nature of the hydrogen being stored. If the tank is meant for a certain pressure and if you over pressurize it, that could even lead to accident. If the material of the tank is such that it undergoes embrittlement, so that is not a proper choice of material, then it can undergo embrittlement and finally a failure. It could be boiling liquid, expanding vapor cloud explosion. If there is a liquid hydrogen release into the environment, that liquid hydrogen converts into gaseous hydrogen, it evaporates. The volume that it will occupy will be 800 times that of the liquid hydrogen. And if it comes in close contact with an ignition source. At that time, it will form a cloud of fire. So that could be another possibility if there is a leak from the liquid hydrogen tank. Sometimes that happens is that some accident occurred at a distance and the shock wave caused another accident at the hydrogen site. So these are all the historical accidents that would have happened. And above all, most of these experiments have been because of the human error, where the protocols have not been followed. The required protocols have not been followed. Now, the major problems lies because you cannot identify it. It is a colorless gas. It's an odorless gas. You cannot detect it by using human senses. Unlike the LPG which we get, there we are adding odorant. However, here we cannot add an odorant because the diffusivity of hydrogen is so high that the odorant will not move as the hydrogen will move. So as such, it cannot be detected by human senses. That is the major bottleneck. And that could lead to certain catastrophic events, like there could be physiological hazards, asphyxiation. Hydrogen displaces oxygen very fast. So when it is a leakage, then it will remove oxygen and the person may feel breathlessness. It can also cause overpressurization onto certain organs. It can lead to thermal burns if there is a fire. It can lead to, if liquid hydrogen is spilled, then it can cause cryogenic burns. It can lead to physical hazards, which is in the form of embrittlement, whether inside the tank, whether outside the tank. So it could be environmental, internal, or hydrogen reaction embrittlement. And that all these can be taken care of by proper coating of different materials, eliminating the stress regions inside a tank. And we can have proper additives being added. Or it could be chemical hazard, wherein because of the leakage, there has been some explosion or fire or a combined, an unignited release, and finally that has finally led to a vessel rupture. So there can be reactive as well as non-reactive type of chemical hazards that can be possible. But there are standards which are available. So at hydrogen usage, these standards need to be followed, and these accidents or hazards can be avoided. Now, when such an incident happens, there is always a lot to learn, and that's why there is an entire record of past accidents, and there is an entire team of researchers like globally which study those as the accidents, and they see like what went wrong at that point which we need to avoid in the future. And that is what is the discipline of hazard evaluation. So in any incident, go back into the past, see what were the reasons, come up with the findings, and make it a standard that this should be avoided for any future usage. And that is one method of doing is event tree analysis, where what we do is we see what was the failure, reason of the failure, what initiated that failure, and what has led finally to an incident. So what has led to propagation of that error, finally leading to an accident, explosion, or a fire. So what we do is we make an event tree, and the process is known as event tree analysis, which is basically a logical model which is developed. And that is a graphical model which portrays what are the combination of events, what are the circumstances under which that accident has happened. What we do under that is we determine what was the initiating event which started, whether it was a small leak, whether it was a ignition source which was available, whether it was an embrittlement, a propagation of a crack, whether it was an overpressurization, what started that event. Now, sometimes what happens is that started, you identified, you rectified, and that stopped. Sometimes it happens is there are sufficient environmental conditions which even led it to further propagate, and that can lead to accidents. So in event tree analysis, we determine what is the initial event that has occurred in different kinds of accidents. Then we see what are the parameters that are affecting the event, initiating event, whether it is stopping that at that point or whether it is further propagating it further. So on the basis of that, our event tree is constructed, considering the initiating event and the parameters, how they are interacting. And then finally, we come up with the results that these are the findings and these are the things that needs to be avoided. So this is one typical example of an inventory analysis, although we will not be able to go into detail because this requires certain terminology. This is an event where if there is a leak or rupture, whether it is immediately getting ignited, so you have an ignition source, or whether you don't have. If you have an immediate ignition, then whether that vessel or tank, or whether that the hydrogen which is confined, it is in a confined space, in a closed space, whether like the car is parked in a parking, or whether it is in an open parking or parking space, just to give an example. Whether it is in a confined space, it will behave differently. Whether it is in an unconfined space, it will behave differently. In an unconfined space, hydrogen diffuses very fast. So there are very less chances of incident. And if there is no ignition, then whether it is getting accumulated and thereafter some incident is happening or not happening. So based on all these judgments, we come up to a conclusion that, see, these are the protocols that needs to be followed. A trained manpower, a do and to-do list is always there that needs to be followed when hydrogen is being used. At any point, at all the points, whether it is in production, storage, transport, distribution, or usage, that protocols needs to be followed. So thanks. I briefly summarized what are the different storage methods, technologies, how we can transport it, and what we need to be careful about while using hydrogen. Thank you.
Thank you so much, ma'am. It was really a very interesting session. Now, shall we take the questions?
Yeah, sure.
Okay, ma'am. Ma'am, the first question we have, how can we use hydrogen as domestic fuel? Is there any possibility?
Yes, because we are using LPG. Same way we can use hydrogen. At present, people are also trying to use as a domestic fuel. And currently what they are trying to do is, because our drastic change cannot happen. So what they are doing is they are blending it. A certain percentage of it they are blending. But definitely because it ignites, it combusts. So it can be used in IC engines. Then it can also be used for domestic cooking as well.
Ma'am, in this regard, one of the concerns is like unequal rate of burning of hydrogen. So will it affect this process, like when we are using it as a domestic fuel? If it burns unequally, then is it feasible to do that?
See, that is in fact, it's not unequal burning. It is in fact, it homogenizes very fast. So whenever you are using, it will homogenize very fast.
Okay, thank you, ma'am. Next question is, in chemical storage of hydrogen, which is more important? The amount of hydrogen stored in the material or the rate of hydrogen released from the material?
Actually, chemical hydrogen storage, these are already there, like both. The rate is also good from chemical hydrogen storage. At the same time, the capacity of storage is also very good. The problem with chemical hydride, which is more important and of concern in current context, is the reversibility. So putting back that hydrogen, any fuel, any material can be sustainable only if you put that hydrogen back and get the initial compound. And that is the major problem there. So capacity is usually in fact higher than the metal hydrides in chemical hydrides or complex hydrides. And the rate of release is also pretty high.
Thank you, ma'am. Yes, ma'am. Ma'am, next question is, do hydrogen storage material have a shelf life? Like they need to be used within a particular time duration?
No, that in materials, that is not a problem. In liquid hydrogen, that is a problem. That I have explained the boil-off losses. So there it can be kept for a certain duration depending upon the capacity of the tank, because that depends upon the surface to volume ratio. And so there it is a concern in dormancy is a concern in case of liquid hydrogen, but not in materials based storage. That is anytime. So you can use it for whatever you have stored until and unless you provide the required conditions for these options for releasing that hydrogen, it will not give that hydrogen. So that is not a concern in material-based storage.
Thank you, ma'am. The last question we have is there any particular advantage of storing the hydrogen in molecular gaseous state? Or does it have any particular application?
Yes, so the advantage of storing in molecular hydrogen storage form is the reversibility of the system. These systems is better. The kinetics of these materials is faster. The release, charging and discharging rate is faster. But the only disadvantage is you require a lower temperature because the bond formed is a weaker bond. So you have to cool it down because room temperature is good enough to release that hydrogen. So advantages are in terms of kinetics and reversibility.
Thank you so much, ma'am, for answering all the queries. Thank you so much for delivering such a wonderful, informative session. And I hope our participants, they have received insight into this new recent topic of research. I also thank all the participants for joining the session. With this, I declare end of the session 2 for the day.
Thank you.